Hello, everyone. Can you hear me?
Yep.
Yes.
Yeah, I can hear you.
Great. How's everyone doing? Whose dog is that?
That's mine.
That's yours? Nice.
Yeah.
All right. Sorry, I'm just on time. I arrived this morning to panic of the machine being down and everything else. So it should be all right. We should be good.
Okay.
I think. Okay, I am recording this. Looks like it's, so I'm going to be able to share that file later. Are we waiting on more people? Should we get started or wait a minute?
I would say if you got some introductory remarks or anything that,
Yes.
just go with that. But yeah, if I assume you've got a lot to do, so start whenever you need to. So.
Okay. Yeah, so we're gonna have two sessions, right? One today and one next week. So I think today we're going to do, well, I mean, we're going to use the machine, of course. It's not going to be just theory, but I do want to cover a little bit about theory of background, about how an electron microscope works and how EDS works, and then we'll do some imaging and some EDS. And next week we'll just, build up on that and just do more EDS on the samples and everything. I'm troubleshooting at the same time I'm talking. It looks like we're going to be okay. But that's the first thing to remember, I guess. Scanning electron microscope and all electron microscopes are vacuum systems. And vacuum systems need to be pumped 24/7, not left open like my machine was all night, because then it takes a little while to recover. And that's what I'm doing right now, trying to pump back to a vacuum that's good enough that we can start. So I think we'll be okay. It's going to take a few minutes, but we'll be all right. I recognize some names. So some of you have already a lot of hours of me talking about SEM. So it's going to be a lot of repeat for you. I apologize, but I guess it's good. It reinforces what we've seen in the past, right? All right, so maybe we'll just get started, right? So, okay, what I want to do first today is show you the machine that we're going to use, explain what an SEM is, how it works, and then I'll share the screen and we'll do a little bit of imaging. Then we'll move on to EDS, okay? Okay, the machine has just recovered, that's good. So here we go. I have a long USB cable, so I'm able to move around. First, I want to show you the machine we're going to be using. And can I want to make sure, yes, I have the main screen, right? So here we go. And you see this, the side of it is open because I had some maintenance to do this morning. So here we go. This machine is what we're going to use. You see lots of monitors, lots of PCs. That's what we're going to use. All right. If some of you have used scanning electron microscopes in the past, you might see that this one is a little larger than what you may have used. And that's because it's not just an SEM, it's a fib SEM. This one in particular is a dual beam. They call it dual beam. It has two beams, an SEM and a fib. So maybe we'll talk a little bit about fib next week if we have time. I think it'd be good to do, just to complement what we're going to see. But just ignore that part for now, and we're just going to talk about scanning electron microscopy. So I'm going to share the interface. All right, can you all see the interface of the microscope? Should look like those 4 windows. It's divided in 4. Okay, good. Mm-hmm. All right. So before we get to that, that's what I was talking about when I was troubleshooting. This is a little vacuum schematic. So when we talk about scanning electron microscopy and electron microscopy more broadly, I mean, of course, it means that we're going to use electrons as the signal, okay, to image. When you do light microscopy, when you use a stereo zoom microscope, a compound microscope, you're using photons, right? You're just using regular light, or at least maybe a special wavelength if you have a special light source. But pretty much the idea is that because you're using a signal that has a wavelength that's in the few hundreds of nanometers, you cannot see something much smaller, right? When you start using electrons, you pretty much get rid of that limitation, because if you consider the electrons as a wave, we're talking about such a small wavelength that doesn't become the bottleneck anymore, and it's not an issue. The wavelength of the incident signal and the signal we use to image is not an issue anymore. What becomes an issue is really the way the system manipulates those electrons to form an image. So because we are using electrons to create an image, we have to have the whole system under vacuum. Because if you had this in air, you would have the electrons just scatter on all the air molecules and everything. You would not be able to control the signal. Plus, it would arc, right? I mean, you would not be able to work like that. So every electron microscope has to be under vacuum, and it's a very good vacuum, okay? So actually where the signal, where the electrons are generated at the top of the machine, it's a really high vacuum, ultra high vacuum it's called, and we never open this. It's always pumped by some turbo pumps and backing pumps, I mean 24/7. So it says gun, so usually it's called an electron gun. And that's what we have here at the top. Green means it's good pressure. So you have electrons that are generated at the very top of the microscope column. And that, I can show you an image of that. Let's just do that. I'm going to go and find an image of that online. Share this. Here we go. So you can see Google here. So there's different types of emission or electron guns. The basic one is something like this. It's just really think of it as a bulb, just a little tungsten wire that you heat up really hot and it starts emitting electrons. That's the cheapest one. This simple geometry or technology. I mean, you can already start seeing some features. I would say maybe 100 nanometers. So that you can already see things that are much smaller than what you could see with an optical regular light microscope, right? And then if you have more money and you need to see smaller stuff, you can buy different types of sources for the electrons. And that's what we have today. We have a field emission gun, so a FEG, field emission gun. And instead of a tungsten filament that just heat up, you have a very, very, very sharp needle at the end of a tungsten, sorry, and it's just an electric field, so it's field emission that's just pulling electrons out of that tip and then throwing down those electrons down the column. Yeah, it can look like this. Really, really sharp. Okay, so if I show this, here we go. That's a good view. Maybe a better one here. Here we go. Oops, sorry. So the electron gun, we just talked about it, is at the top, okay? And then think about your light microscope that's using a bunch of physical lenses to just try and illuminate, the right region and have a good signal. It's kind of the same idea here, but because here the electrons are charged, right, and negatively charged, you can actually play with them pretty easily because you can deflect them just by using either magnetic lenses or electrostatic lenses. You can push them to the side and that sort of thing. You can control them. So usually in an SEM, at the top, when you generate the electrons, and then you shoot them down the column, and then you have a series of lenses and apertures that are trying to pretty much make a beam that ends up being a very small spot. You want all the electrons to land on exactly the same spot at the surface of your sample. That's how you can have a really nice, high magnification imaging session, right? And I talked about before the limitation of the wavelength of the signal for light microscopy. You see here that the limitation is not going to be the wavelength of the electron. It's going to be like how good is your system, pretty much how good the lenses are and all that alignment that makes it that you have a very, very small spot size that lands and you can control it so you can image where you want. Okay? Everything under vacuum, of course. Any questions so far? No? All right. So here's the interface of this machine. We have a Thermo Fisher instrument. So this interface that's divided in 4 little regions that we can put full screen if we want to. That's really typical of the Thermo Fisher brand or FEI before that. And you can see we have a live view of what's in the chamber. Okay, I mean, it's in vacuum, so of course, you can't really look at it. There's no viewport in this machine. So you rely on a camera, the infrared camera that's inside the chamber. And I loaded some samples in there. One of your samples, of course, and then I have also something kind of like basic alignment sample that we get with the instrument. I just want to start with that because it's easier to explain how the SEM works. Okay, and then we also have a top view. It's a photo I took before that helps you navigate from sample to sample or region to region. Okay, so what I want to do first is I want to go on that sample here. So I'm just going to double click on it. And I hope the quality of what I'm sharing is not too bad for you. You can follow. So pretty much I'm just going to go right here and we're going to look at this. So the first thing I have to do is to turn the electron beam on, right? So the vacuum is good. It's all green here, so I can turn it on. I'm going to go right here and click beam on. I'm not sure you can hear that, but it was just a click. And then the beam is on. That means that right now is the source at the very top of my machine is generating electrons, and they're not arriving at the sample just yet because it's paused. But as soon as I'm going to unpause, you will start seeing that rastering of the beam. So we do this. Well, maybe it's too dark right now, so I need to change a few things. Here we go. All right. So right now, you can see that it's out of focus. What I want to do first, though, is make sure you can tell that. Here we go. I'm not sure how it looks like on your end. What I'm trying to show you is that line here that's just going down, right? Also, I want to make sure that you can see, yeah, the maps. Okay, that's good. So you see that line that's going down, okay? So this is how an SEM works. The machine is creating that very, very small spot of electrons and it lands on the sample, right? And then it parks the beam there. The beam stays there for a certain amount of time. And during that amount of time, some electrons are coming back out of the sample. Some of them from the sample, some of them from the incident beam. And those electrons coming out are collected by a detector. And if there's a lot of electrons coming back, you're going to have a brighter image. If there's not a lot of electrons coming back, you're going to have a darker image. Okay? And then after it's done doing that for a certain amount of time, it goes to the next spot. That's what creates your pixels. Okay? So of course, the amount of time that it stays in one spot is super fast. Right now, it's actually pretty long, but it's only 5 microseconds. Okay? So the beam pretty much does line by line, spends 5 microseconds on every single spot, and just plots or gives me a signal brightness based on how many electrons it's collecting during those 5 microseconds. So everything you see in electron microscopy are just images that are intensity maps, okay? And that's why you never have colors. So everything you see that's colored or yeah, with colors, it's always colorized. Post-processing, Photoshop, all of this. Or it's EDS maps, and we talk about this later. There's a strong push right now to sell color SEMs, and don't think it's an SEM that sees things in color. It's not that at all. It's just coloring based on composition. So we'll do that later. So that's pretty much what just an SEM is. It's a scanning electron microscope. So it's just scanning line by line. And I control the beam. I control where it focuses. I control how fast it's scanning. I control brightness, contrast, all of those things. Okay. So right now, I'm imaging the sample that's right here. Okay. And I can focus the beam so that it lands in a tiny spot exactly at the surface of my sample. The reason it's not focused right now is because the electron beam is focusing at a distance of 7 millimeters away. So think about it as your light microscope that has a lens, and you have to move the sample to the focus plane because you have to, meet the focal distance of the lens. Here we can do that, same as a light microscope, or we can just leave the sample where it is and just turn the focus knob on the machine, and it will just change the focus distance of those electrons. So right now, that's what I'm going to do. I'm just going to turn the focus knob until this distance makes it so that the electron beam just lands here. So this is 4 millimeters here. So right now we're focusing about here at 7 millimeters. So I'm going to have to go at least, something like 15 millimeters to get to that plane. So I'm going to slowly turn. I'm turning the focus knob right now, and you can see the distance is increasing, and you can see things are coming into focus. So all I'm doing right now by slowly turning the focus knob is trying to make sure that the electrons land in a small spot at the surface of my sample. And here we go. Yeah. About 16.8, that makes sense, right? That's that distance here. All right. Now I can move around by double clicking. I'm going to do so. The electrons are are just being moved around from here, this corner here, all the way down. If I turn the magnification knob that I have in front of me, it's just going to tell the machine to only scan them from here to here, for example, and this is going to become my new field of view, and that makes it, more magnified. So I'm going to do that right now, just turning the button, and that's it. You can tell that my focus is not so good, so I'm just going to turn the focus knob again and try to get something a little better. And here we go. Okay, so what we're looking at is tin, little spheres of tin. I'm going to zoom in another spot here and refocus a little bit. All right. You can see it's very easy to get to really high magnification pretty fast. I mean, I'm at 2500 already, and zoom in more easily. I'm in the shadow of that big sphere, so I'm going to move it a little bit. So we're not really spending much time trying to align things, but I'm going to pause this. You can see that I can already see little spheres that are in the order of 200 nanometers and much, much smaller, just in a matter of a few minutes or a few seconds, right? So this is how powerful an SEM is compared to a light microscope. Do you have any questions so far on how the signal is generated and how we can get images from that? No? Okay. Just feel free to interrupt at any time. I should be able also to see the chat, so you can also type things if needed. Okay, so let's move on. So this is how you image. Of course, I can change the scanning speed right here. That's how long the beam spends on each spot. That just, if I go to a super short amount of time, only 100 nanoseconds, it can just go through the all the pixels much faster. But you see how grainy that is. If I tell the machine to take its time and acquire more, spend more time, it's going to be able to get much finer images. I can increase the resolution, so more spots to scan, and things start to look much better. And that's how you take images. All right. Now, one thing we haven't talked about is those values here. I'm going to pause for a second. So when I turn the beam on, I just said, okay, filament, start making electrons, and then I use whatever settings were already there. But you actually have more control. You can decide how much momentum you give to those electrons as you shoot them towards the sample. Okay, so when they are created, obviously electrons are negative charges. If you put a strong positive charge right next to the filament, you can grab those electrons and really shoot them down with high momentum down the column. Okay, and that voltage that is, giving that, or that pulling, force on the electrons to just give them energy and momentum. This is what is represented here by that high voltage. So most SEM, pretty much every commercial SEMs, they can go all the way up to 30,000 volts, or 30 kilovolts, 30 kV. You can see I have presets from 1 to 30. I can type whatever I want, but those are presets. Right now I'm using very low energy. So the electrons that I send to the samples are not super energetic. And it's good for surface sensitivity. We'll talk about this, but just know that you can bump that up all the way to 30. So I guess the question is, why would you use, when to use a low voltage or high voltage, right? So we will see that when we do EDS, we will need high voltage, and I'll explain why today. But just keep in mind that this is the energy, it gives the energy to the electrons. So if an electron has a lot of energy, it can penetrate deep into the sample. And as it penetrates into the sample, it generates signal from the sample. It generates electrons that we will use for the imaging that we're doing right now. We capture those electrons, that gives us the image, but it creates other stuff. And one of those things that it creates as it interacts with the material is X-rays. And those X-rays are the one that we're going to capture, and that will do the that will be the EDS technique. That would give us an idea of the composition of the material. Okay, so if you use high energy, you can actually generate a lot of signal, and you can interact with a bigger volume. The electrons penetrate deeper. Okay, if you reduce the energy like I have right now, if it's pretty low, the electrons that I shoot to the sample, they stay very close to the surface of the sample. So it's more, you get an image that's more surface sensitive than if you have a high voltage. So I'm going to try to illustrate that. So this is the image I just took at 2 kilovolts, and you can see a lot of little stuff at the surface of those. I'm doing it live. I'm not sure if it's going to work, but I want to try to do 30 kilovolts and see if we still see those at the surface of the spheres. So I'm going to go on this side of the screen. That's convenient that we have all those four, because you can start comparing stuff. Yeah. Do a quick focus here. Try to do the same settings. Here we go. So as you can see, at 2 kilovolts, you can see very, very fine, shallow features at the surface of those spheres. At 30 kilovolts, you don't see them too much, because the incident electrons that I send, they interact with the surface, but also a little bit deeper into the sample. And the signal that you collect that comes from the sample is an average, right, of what is coming from that spot that we interact with. So if the signal comes also from what's below the surface, you lose surface sensitivity. So if you ever use SEMs, just make sure that you select your voltage appropriately, because if you use high voltage, you might lose a lot of the surface detail that maybe you're interested in. you have any questions? No? Well, I'm going to ask the question then. Why not always use low voltage if we're going to lose some sensitivity with 30 kV? Well, two reasons. The first reason is that higher energy means shorter wavelength of the signal, and shorter wavelength means you can see smaller stuff. So at 30 kV, at the maximum energy, you can distinguish, or you can differentiate smaller objects than at 1 or 2 kilovolts. So that's reason one, which makes it a trade-off. If you're trying to see small things, you need the voltage high enough to actually be able to see it, but not too high that you lose surface sensitivity. So that's why when I train people on the instrument, I tell them, you just don't be afraid to explore different voltages from low to mid to high, because you want to see what works best for your sample. Of course, the interaction in the sample is going to vary depending on your material. Is it light elements? Are those heavy elements? It's going to be different. Second reason why sometimes you need high voltage is when you do EDS, like we'll do in a few minutes. You need for EDS to have the electrons being energetic enough to actually create the X-rays. If they are not energetic enough, like at 2 kV, you just don't create the X-rays, so you cannot analyze your sample. That's simple as that. All right, let me think if we covered enough to go to the next step. Okay. The next thing is the beam current. And again, we're shooting electrons to the sample. So we're making a flow of electrons. That's a current. So that's what it's measured here. If you tell the machine to use a low current, it's just not going to send a lot of electrons per second. If you select a high current, it's going to be more electrons per second. And because there's more electrons per second, there's a lot more packed in the beam. It makes the beam and the spot on your sample a little bigger. So you start losing resolution. So for example, here, we have this image. Let me try to bump that to a really high current. See if it still looks decent. It's pretty low magnification, so it should still look decent, but not as good. Try to focus it. See, it's not as good, right? Because the spot that is scanning is just bigger, so you cannot distinguish very fine details if when the electrons land, they just probe several regions at a time, okay? So when you do imaging, you want the low current. So why would you need high current? Well, same thing as we talked about. If you're trying to do some EDS, some composition analysis, any of those analytical techniques, they need to gather a lot of signal. So if you go with a low beam current, you don't generate a lot of signal, and it's going to take you hours to do anything, whereas right now it would take you a couple of minutes. So everything is a trade-off here. So I'm going to bring that back down. All right. One thing I haven't talked about is conductivity. So of course, we are shooting electrons to a sample. So we want, in electron microscopy, we want the sample to be electrically conductive. So right now, this is tin, right? If I zoom out and I go, like right here, that's the holder, that's aluminum, okay? So no problem, I don't see a lot of issues, okay? Now, just to compare, I'm gonna briefly go on the embedding compound. I don't know if it's acrylic, like it's not bakelite, but it's whatever you use to embed, and you can start seeing lots of weird things happening. So what you're seeing right now is that you actually see a mirror developing. So I'll take an image of that. What's happening is that right now, because this material is not electrically conductive, I'm sending a lot of electrons into the sample, but the sample has no way to get rid of them. Okay, so they accumulate into the material, and right now they stay there. So the surface of the sample becomes negatively charged, and it's turning effectively into a mirror. And let me reduce the voltage, and I'll try to make a nice mirror. See if it Here we go. All right. So for an insulator like we have now, I loaded so many electrons in there again that the surface became negatively charged. And as I reduce the energy of the electrons, they don't have a lot of energy, obviously, just 2 kilo electron volts of energy. And as they approach the surface, they feel that charge on the sample, and they actually don't even land. They just go back up and they hit whatever is above the machine, above the sample. So what we see here is actually what's above the sample. We see the pole piece, we see the detector right here, we see the tube and other stuff, we see cabling and all of this. So I turn the sample into a mirror by doing that. If I zoom out, you can see, let's see, I think it's slowly closing on itself. All right, ready? Hop, the mirror has disappeared. And now we see the sample. So, of course, our goal is not to make mirrors, right? We want to image our samples, even when they are not electrically conductive. So we have tricks, and I'll talk about them in a second. I try to make the sample a little bit conductive, and you can see it's able to dissipate charges because I waited a little bit, and that mirror pretty much closed on itself, which means that the charges were dissipated. So this sample has the capacity of and the ability to just get rid of charges. That's good news. But you see how everything kind of gets complicated. You see weird contrast and everything. That's called charging effects. You are charging negatively the material. Everything gets super complicated when the sample is negatively charged like this. So to try and make insulators conductive, we have different techniques. We can use, let me make sure, stop sharing and show you some tools. So we can use like tapes like this, just copper tapes. We have some conductive paint. This is graphite paint. So you just paint the surface of your sample and the solvent leaves, and you leave behind some conductive layers. Of course, you don't want to paint the surface of your sample, but close to it, you just want to give a path for the electrons to go somewhere. And another technique is to deposit a thin film, a thin metallic film at the surface of your sample. Of course, not too thick, otherwise you hide what you want to see, but just thin enough that it can actually conduct electrons away from your sample. So that's a machine we have down the hallway. It's called sputter coating. And you just put a few nanometers, not microns, nanometers. 5 nanometers is typical of gold or platinum or something at the surface of your sample. And that helps with, imaging insulators. But you can tell, how it was so easy to deal with tin, for example, or aluminum, and how difficult it gets when you get to that embedding material, or we'll get to the glass rods, of course. That's a bubble. Once you get to the glass rods, it gets a little difficult. Where are they? Yeah, we'll find them. That's one here. Here we go. That's the edge of one of the glass rods. So you can see here what I've done is I took, what was embedded, and I just sliced it, and I did a rough, grinding and polishing. I think I went just down to briefly 1200 paper grit, and then just 6 micron, just to have something that would be flat. That's important for imaging and for the EDS, for the composition. So we'll have a look at that. All right, so I want to talk about EDS. If you have no question about how we form images and that sort of things, Any questions? Sorry, I'm trying to reply to something. Okay. I was mentioning we have several equipment that are down, so I'm trying to coordinate repairs. Okay. Let me stop sharing this, and now I want to talk about EDS. So an SEM, I mean, it's doing imaging, right? When we talk about doing some EDS, so EDS is energy dispersive spectroscopy, that's just analytical tools that you add to a microscope. When you buy the microscope itself, it doesn't have those tools. Those are the composition, the EDS, that sort of thing, it's an add-on. You just buy extra detectors. The signal is always there. The detector that you buy is able to capture that signal. So you might very well use SEMs in your future that do not have that EDS capability. I would always recommend someone who buys an SEM to just add that capability, even low budget detector, because it's very powerful. But it's possible that you have an SEM without EDS. Now, you can never have EDS without an SEM. You need to have those X-rays created, and you create them with the electron beam. If some of you have used XRD, you know a little bit about, if you know a little bit about how the X-rays of the XRD are generated, it's actually the same way we generate X-rays here. So you have an electron beam that just hits a material, typically copper in an XRD, and it creates copper X-rays, and then we use those to do X-ray diffraction. Well, here we don't go all the way there. We just have the electron beam. When we image, it hits our sample that's the unknown, or maybe we know what it is, or we want to analyze it, and then we get the X-rays from the sample, and that's it. We just see what's in there. So that's the idea. So let me find a good schematic to share. All right, so if I go, I have this open. Do yes. Those are classic images of what's happening in the SEM. All right, so this is your sample at the bottom. The electron beam is what we shoot to the sample, and depending on your energy, so the accelerating voltage that you select, is going to penetrate deeper or not. But when it penetrates, it interacts with that whole volume here, okay? And what it's showing you, all the signal coming out, it's very important to understand that this is always happening. Whether you have the detector to capture specific signals or not, it is happening, okay? So you have different types of electrons coming out, secondary electrons, backscattered electrons. I'm not going to get too much into the details, but we use those for imaging. Auger electrons are very, it's a signal that's very surface sensitive. We cannot use that in our machine, but that's a way to identify composition of your sample. X-rays are coming out. That's what we do today. You say it says EDX. EDX and EDS is the same technique. It's energy dispersive X-ray spectroscopy. So we will capture those X-rays and get composition. Cathodoluminescence, another technique, we cannot do that. That's more for geology. You have different light that's emitted, different photons, some in the visible range, some not, but they can be captured, and you can get really nice images, colored images that tells you some things about the minerals that are involved. And you have also a lot of X-rays that we don't want, but we get them, and that's just the German name, the Bremsstrahlung. That's just the continuous radiation. It's just the background noise when we do EDS, so you'll see that too. If some of you have heard about TEM, transmission electron microscopy, it's a different machine using the same concept with electron beam, an electron beam going to the sample, but you only use samples that are very, very thin, so that the electrons actually go through and you get what's coming out of it. So the transmitted electrons, and you get a lot of different signal that is, how the electrons scatter when they go through your sample. So we're not going to do that today. If something that's something that you're interested in, you can you can always come to the EMC. We have a transmission microscope, and you can have an idea what it looks like and how it operates. Okay, so far today we've only talked about the incident beam and then the electrons coming out. Now I want to talk about the X-rays. So again, X-rays are always coming out. The thing I mentioned briefly is that you need to have the incident electrons strong enough that they can actually excite those X-rays. So if you use the Bohr's model to talk about an atom, you have the nucleus, and then you have those shells of electrons, KLM. When you shoot the electrons from the incident beam, if they are energetic enough, they can actually break some bonds here so that you can free some electrons from your atom and it flies away, okay? Like this one on the K shell. It's flying away. This electron is one of those that we capture that form the image, okay? So that's what we select with our electron detector. That's how we form the image. When this electron leaves the atom, of course, the atom is in an excited state, doesn't like it. It's missing an electron here. So it really quickly reorganizes itself and gets back to a non-excited state. And to do that, it's having one of the electrons in a higher shell just jump to fill that vacancy. Okay, that's what's represented here. So in that case, it's from the M shell, but it could be from the L as well. So this electron jumps in and fills that emptiness that was created by this electron leaving. And this jump releases energy in the shape of a photon, an X-ray. Okay, that's how the X-ray is created. And that is the X-ray that we are capturing in EDS with a special detector. Okay. So when I was saying that you need to have the energy of the incident electron pretty high for EDS, is because you want to break that bond here between the electrons that are close to the nucleus and the nucleus, right? You want to free that electron so the whole mechanism can happen. If your incident electron is too weak, maybe it's going to be able to, eject some electrons from, those energy shells that are not, the energy is not very strong, the bonding energy is not very strong. But most of the time you just cannot excite the X-rays, and then you just simply don't have any signal to analyze. So what you want for EDS is you want the energy of the incident electrons to be about twice, preferably even more, but at least twice the energy of the energy of the X-ray that you are trying to see. So let me go back to the camera. Every single atom is generating X-rays that are characteristic of the atom. Okay, so an iron atom is not going to give X-rays that have the same energy as a nickel atom, for example. That's how you can identify what element has been generating the X-ray. And that's how you identify the composition. So usually you can find in every SEM room, you can find tables like this. Sorry, it reversed, but you have all the elements, and it's actually showing you the energy value of the X-ray X-rays that are coming out, so you know where it should be. Now, of course, the EDS software will show you that as well, but just know that the X-rays are characteristic. That's how we can identify things. So let's do it. Let me connect to the EDS computer. Again, I was mentioning that you buy the detector as an extra to put on an SEM. So in our case, it's not the same manufacturer. So we have a different brand, a different computer, and all of that. So I'm going to connect to the other computer now and share that one. No question? Still nothing? Okay, I'm going to close this and save it later. All right, so this is the interface of the EDS computer. This is the EDS software. So the first thing we're going to do is insert that EDS detector. So I'm going to be juggling back and forth between the two computers. Hopefully it makes sense. But right now in front of me, I have two computers. I have the one for the EDS that you see here, and I have this one, the one where I control the machine, right? So what you need to do is position your sample under the beam, focus in all of that, and when everything's ready, then you go to the EDS software, and then the EDS software takes control over the beam and moves the beam and captures the X-rays. But first you have to position everything here. So we're going to do that first here. I'm going to go to an easy region. So I think I'm going to go back to, oh, maybe I can go. I put a little piece of copper here. So let's go to that one. See if it's not too bad. Yeah, not too bad. So let's first practice on copper. So you can see I'm on the copper tape. It looks like this, not very clean, so probably lots of contamination, but it's okay. It's good for practicing. The first thing I need to do is move it up a little bit, because in this machine, we like to work with everything 4 millimeters away from this. So it's just specific to this machine. It could be different in another machine, but everything is calibrated for this distance. So first thing is I move them. And then I need to insert the EDS detector. It's retracted now, so I need to do that. Go here and click in. I'm going to go back to the microscope PC, and you will see it coming here. Okay, wait, here we go. That's the EDS detector. So of course, it's trying to get very close to the sample because you want to capture as many X-rays as possible. So it needs to be very close and just collect as many as it can. All right. So there's going to be a lot of back and forth, but be okay. Let's go to Oxford. Here we go. So right here, I want to do EDS, no problem. I'm just going to do a quick point analysis. You can type a lot of things here, but I just want to go straight to the point. First thing I'm going to do is grab the image from the other computer. So let me increase a little bit the scanning settings. Here we go. Click here, and it's taking over, and it just took the image that I had on the SEM side. Okay, and once I have this image, I can go to the next step here, acquire some spectra, and I can decide if I want to do point scans or area scans or whatever shape I want. Pretty much the machine knows where how to manipulate the beam to only collect X-rays from a certain area. So if I make this box here, it's going to raster the beam, the electron beam, only inside that box, so only on that region of the sample, and it's going to collect all the X-rays coming from that region. So I'm going to do this. And at the bottom here, you see the spectrum. Okay, so the x-axis is the energy of the X-ray that's being measured. Vertical axis is pretty much some intensity. What you can see right away is that I'm only measuring within 2 kilo electron volts of X-rays, and that's not good, because if I know I'm on copper, I just know that, but copper has, and I'm looking at the table I showed you earlier, copper has X-rays at 8 kilo electron volts, right here, and I don't see them. And the reason I don't see them right now is because I'm using a beam that only has 2 kilovolts or 2 kilo electron volt of energy. So because those incident electrons only have 2 kilo electron volts, they will never be able to, create X-rays by displacing or ejecting electrons that are, really tightly bounded to the nucleus, right? So we need to bump that up. I mentioned at least twice the value. So if I want to see copper 8 kilo electron volts, sorry, I need to bump that up to at least 20. So I'm going to do so right now. All right, I'm at 20 kilovolts here, so 20 kilo electron volts, electrons. I'm going to take the image again, a little bright, it's okay, and make another box. And now you see that I can measure pretty much everything up to, well, technically up to 20. But again, I want to only look at things that are the first half of my accelerating energy, okay, accelerating voltage. Now you can see the peaks I was talking about. So again, the beam is moving everywhere and we're collecting X-rays. It's showing you here how many X-rays per second and all of that. If I go to the next tab, I can identify those things. So if I double click on a peak, it's going to suggest copper. You see copper has several peaks. Why does it have several peaks? It's because depending on what electron, what shell the electron has been ejected on, what shell it was, and what shell the electron that's filling that vacancy, what shell did it come from, that's going to change the X-ray energy. So you have, it's all happening kind of randomly. So you have several peaks happening. Okay. So I can move around and try to find other peaks in the background. There's a little one here, carbon, little one here, oxygen. I mentioned that the tape wasn't super clean, so you have some hydrocarbons on it, some oxide, something. So it's always there, and that's something you have to fight all the time. But you're always going to have a little bit of carbon and oxygen on pretty much every sample. You could say maybe there's something here, aluminum. That's where you start having some issues because it's very likely that it's coming from the surroundings. Remember, we shoot electrons to the sample. Some electrons just bounce and go a little bit everywhere in the chamber, and they can excite things that are not your sample, but the surroundings. So it's very minor, so I'm not going to worry about it too much. And now the machine can calculate. I'm not going to get into the details. We don't have time about how it's calculated, but the machine is calculating a composition based on the intensity of those peaks and everything. So right now it's telling me that it's almost 96% copper and a little bit of carbon and oxygen, which is just surface contamination. So if you would really clean the sample well before it goes into the machine, would be closer to 100% copper. Still no question?
I don't know if you're sharing your screen.
You're not seeing the EDS?
I'm just seeing you, Nico.
I should have told me. Thank you for telling me. Oh, let me see. Yeah, it just stopped working. Okay, let me see. Can you see it now?
Looks good.
Okay. Well, let's get back and do that again then. Please tell me if you don't see the screen when I'm mentioning some stuff like that. So what I did at 2 kilovolts, that's what I did. I don't know if you saw that part, but when I was using electrons of 2 kilovolts, you could only see peaks that are below 2 kilo electron volts. When I switch to 20 kilovolts, I can see X-rays that are technically all the way to 20 kilo electron volts, but you really can only analyze things that are about half that energy. So if I want to see copper, that has a peak at 8 and almost 9, and again, I know where those peaks are based on the table. I want twice that energy for my electrons, so that's why I selected 20 kilovolts here. All right. You could say, oh, I'm going to use 10 because my copper X-rays, it's at 8. Let's do the test. Acquire the image. Make a box, and the electrons will be running in the box, and we capture the X-rays. See, even though I'm sending electrons that have 10 kilo electron volts, that's not strong enough to excite the X-rays that have 8 kilo electron volt energy, which doesn't work. So right now I would be missing those copper peaks. So make sure you use an energy that's twice as much, a little bit higher. So again, I put 20 kilo electron volts of electrons, grab the image in the EDS software, make the box where I want to analyze, and now I can see those. Of course, it's very easy right now because I know what I want to study, right? I know right now that I am looking at that copper tape that I put on the sample. So the question is, what do you do when you have no clue what your sample is? If you have a true unknown sample, well, a good thing to do would just put the maximum voltage you can on your machine, which is 30 kilo electron volts. So if you put 30 kilo electron volts on your incident electrons, you're going to be able to visualize, nicely excite X-rays all the way to 15 kilo electron volts. And 15 kilo electron volts, you're going to be able to see pretty much everything in the periodic table at some point. Okay, so that's if you have a completely unknown sample, you start with that. And then you can always reduce if you have to. For example, if the sample is not conductive, like we'll deal with in the second hour today, because you have glass, right? Glass embedded in something that's not conductive as well. Okay. So that's EDS pretty much. A lot of, I mean, it gets more complicated than that, but it's a lot of just, point and shoot pretty much. If you want to know what's in, oh, I think it's still running another one. If I go back to another spot, let's say I go here. Zoom out a little bit. Yeah. Let's see what I can get from that. I have the holder and the screw here. I can go to the EDS, grab the image from the SEM, and then I say make a analysis right here. Again, the beam moves in there. I can check what that peak is. Double click on it. Aluminum, easy, right? Again, the usual suspects, always a little bit of carbon and oxygen. Magnesium, maybe some alloy. All right. Go back and say what's in there. Oh, not a lot. That's because it's probably, deeper, so it's blocking. We don't get a lot of visibility of the signal, I think. Let's see if we can get a little better by just going away from, yeah, let's try here, farther away from other stuff. So I just moved to see more of the screws and hopefully not be in the shadow of something else, okay? Let's see what we get here. It's too low. See, that's why, let me share the microscope. That's why you have to work, it's recommended to work at 4 millimeters. Now this screw is, I'm focusing at 10 now. So let me bring it up. I want to make sure I don't collide with anything, of course. So I'm going slowly. Go a little faster. So I'm moving the stage up. You can see. It's about as high as I can go. Because I don't have it very high. Let me try to go ahead of the screw. Maybe it's going to be easier. All right. Oh. Okay, let's try this one. Still, I'm at 8 millimeters, so a little far away for this machine. But let's see if we can capture the EDS spectrum from this spot. Yeah, we can. Not a lot of X-rays, but we're still getting something. Looks like it's not aluminum, right? So just check that. Yep, it's going to be a stainless. Yep, here we go. Stainless screw. So having quick answers like that, that's really the really nice value of this technique, because a lot of times you kind of know what's in your sample. You just want to confirm it. You want to identify regions, that sort of things. So it's really a quick technique. I mean, you see how long it takes to know that it's a stainless steel screw. It doesn't take much time. All right. Well, what is it, 10 o'clock? That's pretty much, well, I just want to show the map first. And then we'll maybe take a couple minutes break. And then the second hour, we'll just go on the sample and just start playing on this with your sample. And we'll have more time next week. Before that, I want to show you a little bit more about EDS. So doing a, point and shoot and just get a spectrum on a certain region is nice, but we can do more. Let me try to go to a region that maybe could be more interesting. And we'll do that on your sample, of course, but the sample is a little tricky because it's glass. So let's see what we can do here. If I have partially the copper tape and partially your sample, I'm going to go back to the EDS software. Here we go. And we can do land scans. We'll probably do some of that in the second hour. So let me scan this image. What you can do is, instead of making a box and getting every single X-rays from it, you can just draw a line like this. And it's going to divide that in a bunch of individual steps. And you can get a profile on that line. Let me do some binning here because it's spiky here. Yeah, here we go. So you can see all the copper here. The copper is in purple here. And then, of course, at the transition, it goes down, and you have the carbon from your embedding material that just goes straight up. That's how you can, if you're looking at something that's diffusing into something else, you want to see some sharp transitions. That's pretty much what we're going to do today in your sample, to try to see the evolution with depth, for example. So that's just the line scan option, but it's all the same idea. You have to have enough energy in your electrons and all of that to be able to excite all the X-rays. So if you have a completely unknown sample, first you would do like a quick point to know what the elements are, and then when you do line scan, you can directly select the elements that you want. That's the line scan, and the last thing you can do is maps. So I'm going to do this. I'm going to make a new region of interest again. I selected the map option, grab the image here. I'm going to make a box just like we did earlier, but what it's going to do right now, it's going to okay, just forget about this. Here we go. So make the box. Again, it's moving the electrons everywhere, but in this case, it's going to, instead of averaging all the X-rays that are being collected by the detector, it's going to remember where it's coming from, and it's going to color this region based on the composition. So if I go to the next step and add the carbon and the copper, make it a little bigger, you will see that coloring of the image that is showing you where the copper is and where the carbon is. So those are EDS maps. So I mentioned a little bit earlier about the color SEM that you see on a lot of brochures nowadays. This is pretty much because EDS detectors that we're using today, the newer ones are so fast that they can actually color the image in real time as you image. See, right now I'm making a box and I have to wait, right? And it's slowly coming. I mean, it's coming, but it's going to take a little while, okay? But now it's so fast that you can have that as an overlay live. And that's what they mean when they say color SEM. It's an SEM outfitted with an EDS detector that's just constantly giving you feedback on the composition. That's very powerful because as you image, you can directly locate the region that you want to analyze. You don't have to pause, open another software, make a box, analyze, and all of this. It's just live all the time. Okay. Should we take a couple minutes break and then we'll just continue on your samples? Does that sound good? You're muted. What time is it?
That works for me.
Okay. Let's take 5 minutes, so until 10:10, and then we'll move to your samples, and we'll do EDS, the same thing we've been doing, land scans and maps, and try to see what's what.
All right.
All right. See you in a minute. Okay. All right, so we have 1 hour of background. Now let's get into it. I want to make sure I have, the proper color code. So I'm going to share again the screen. Up, up. Here we go. So we're going to now look at your samples. So I can zoom in here. I want to make sure, I think this is the green and the blue one, and then you have the yellow one here. Any preference which one we start with, or should we just start with this one?
It doesn't matter for me. That one's probably the most likely to see silver.
Okay, well, let's do it. So I pause the beam. I'm going to unpause it, and okay. So see, in that case, for example, it's a case where you kind of know what your sample is, right? I mean, it's glass, so you're going to have some silicon oxide, you know that, and you mentioned silver. What else are we expecting to see in there? And the question is for everybody, right? You should guide me. Those are your samples. Hello. Anyone can tell me what's in their samples? Man, you guys are all shy. What I need, the info, okay. Raj says sodium question mark. I guess silver is what you're trying to see. Okay. Let me see if I can have the chat pop out, because I didn't see the chat earlier that you told me I wasn't showing the screen. Now I can see it. I need the info because I'm using that right now. I'm going to look at the elements you mentioned. I'm going to check the energy of the expected X-rays, and that's going to guide me in the selection of the incident electron energy, right? If you had a piece of metal, I could put the maximum voltage to be sure to excite everything, okay? But because you have something that's really not conductive, I'm going to try to minimize the energy of my X-rays, because if I put super high and it's not needed, I'm more likely to create the mirror issue that I had earlier, right? And that's not just showing you a mirror and it looks bad. It's also slowing down the electrons, so the analysis might not be going very well. So I don't want to use the maximum energy for my incident electrons unless I have to. So I'm looking at my table. Silicon, the main X-ray line I want to see is 1.7 keV, so that's really low. You mentioned sodium is going to be oxygen. Sodium is 1.04, oxygen 0.5, so that's all really low. Now silver, there's a line at 22.1 that's way too high. Remember, I need to have twice the accelerating voltage. I can only go to 30, so I'm not going to be able to excite the 22 line. But there's another X-ray peak or line at almost 3. So that's the one I'm going to look for, 3 kV. If I want at least twice that, that brings me to 6. I'm going to put a little more. I'm going to put maybe 7. That's how it's guiding me. Okay, so let's do that. I'm going to share the screen. So with that discussion we just had, or I had with myself, I'm going to put 8 kV. So it's not in the preset, so I'm going to go here and just type it in, 8 kV. All right. Scan a little faster. I hope you can see. That's the edge of the sample. Focus on it. Make sure it's at about 4 millimeters, right? So it's a little high. I'm going to bring it down. All right, here we go. let's just do a quick scan inside to make sure maybe we can see silver everywhere. So pause that for a second. We're going to go to the other computer. Go back here, and I'm going to make a new specimen. So let me rename that to practice copper. We can just label everything. And should I call it a special name here, or just, I guess, the first one? We're going to leave it. It's a sample one for now. We can always change that later. All right. I'm not going to do a map. I just want to do a quick analysis just to see what's in there, and then we'll make lines most likely afterwards. So first, again, I'm just going to grab the image that is in the field of view on the SEM. So here we go. See, you have lots of weird issues because of the non-conductivity, but it's okay. We have to deal with that. Acquire the spectra. So let's see. I'm looking at some things in there. Okay. I'm going to first make a box like right here. Just see if we see something of interest here. Okay. Go to the next one and just identify. Because I'm using 8 kilo electron volts energy for the incident electrons, I cannot see anything above 8, right? That's why you see nothing here. I'm going to concentrate on those. Oxygen, and you're going to have silicon, that's glass, right? Of course. Sodium, you're right. Magnesium, aluminum, calcium. All right. Your silver should be about here. Okay, we don't see it. I didn't load. Let me check something. It's going to be good to compare doing the cross sections, and then since you brought me also the rods not mounted, we'll also do that. Maybe we'll compare with that if we have time later today or next week. But yeah, we don't really see any silver here. Okay, but I'm inside, right? I mean, we're going to want to study also what's happening closer to the surface, of course. Okay. Also, I'm just noticing here that, you know, I don't know if it's because of just the camera and everything, but it looks like it's not colored the same everywhere. So I don't know how much it's due to that, or maybe the marking, but let's just move around on the sample and see other spots. I mean, it's fairly quick to get a, you know, an answer. So I'm gonna, yeah, you can see I'm just moving around different spot on the same sample. Yep, I'm gonna just make a new spot. So let's just see what's going on here. I'm looking for that peak that's around. Silver is, what did I say? Yeah, it's 2.98. So doesn't seem like there's anything here. Okay, you go to another spot. Let's go over there. Make a little box here. All right, so it doesn't seem that there's much inside. Okay, that's okay. Let's just stop this. So what we're going to do now is let's just try and investigate closer to the surface, right? So what I would do, and I think what we should do, is go here, make sure I share the right screen. I don't want to do the same mistake I did earlier. Okay, and we're going to do a new spot, but I'm going to do the line scan. And let's see. Here we go. Let's see if we see something in the first, maybe 50 microns or so, something like that. me add the silver. See, when you select silver in the table here, it shows you where the peaks should be. I can show them all like this. I can also do something like this so we can see silver better. Yeah, I don't see much. I mean, it shows you spikes, but there's also a lot of background, so it's hard to trust those things right away. Yesterday, I briefly looked at. Let me stop sharing for a second what it's acquiring. So we can just let it grow and see what happens. Yeah, you can see me. So yesterday I looked at those, right? Yeah, Tom, you tell me that I looked at the 5% silver, this one, potassium, this one.
Yeah.
I looked at the surface. I could see silver.
That one should definitely have silver.
Is it the same as what we're looking at now in cross section or similar?
Let me pull up the lab notebook. Because you have sample 2, right?
Yeah.
Or the second mount.
So something that I want to talk about is, I showed earlier that image of the interaction volume and where the signal is coming from. At 8 kilovolts, like I'm using right now, the depth of what's being probed, we're talking about less than a micron. Okay, so that's where you also have to think about those things. If you have the rod just like this, and I put the beam at the surface, the signal, the X-rays generated come from the first micron. Keep that in mind, like 1 micron in depth. So if the silver, or what you try to diffuse in it, is in the first micron, we'll see it. Whereas right now, if I share again the screen, you can see that the scale bar is 250 microns, right? So if you have silver if it's just in the first micron or so, I mean, it's going to be completely lost here. And you could be in that noise here, right? But that's part of it, right? We just don't know when we start. So that's why we have both types of samples. We have the cross section and we have the surface.
So this should be the same sample. This is the 5% silver and potassium.
Interesting. All right. Okay, well, let's just go to another spot. Oops. Let me share the right thing. And maybe I'll just zoom in even more. You see how you have all those weird contrasts happening? I'm sharing, right? Being careful now. Let's make a new scan at a different magnification and try to study that first layer here. So maybe the first 20 microns or so, something like that. Sorry. Sorry about that. I'm back. All right. So even at higher mag, I don't see much. See, the automatic doesn't detect it. Interesting. You might see potassium. So you can see with those, I mean, the more you wait, the more you collect X-rays, and the more, because it's creating pretty much a spectrum at every single spot along that line. I think it's divided in 500 individual spectrum. So the more you wait, the more every spectrum becomes clear, and you can it can decipher peaks and all of this. So it's pretty noisy at first, but again, the more you wait, the better it can get. We start to see also so it was silicon. I was excited. You have some things due to the topography, and if it's a little higher, you can get a little more signal. I don't really see much silver. I mean, I know we see those things here, but it's not something that's conclusive to me. Let's go to another spot on the sample. We can bump up a little bit the voltage, see if we can get a little more signal faster. Let's go this way. All right. Yeah, it doesn't jump at us. I think I added the silver, yes. You do see something here. Let's just wait and see if it's real. But if it's in every element, it's not a good sign. That just means that topography-wise, it's probably more, like it's directing X-rays more towards the detector. So it's kind of a fake peak. If it's in everywhere, that's how you can tell. Just, you have to normalize things. So it's not necessarily a good indication. Do we want to try directly on the rod, or do we want to keep that for next week?
So I don't know if it doesn't look like we're seeing anything
Not anything conclusive
on these samples. Yeah, that might be. I mean, that you said you already looked at it in that way and you saw some.
I think I saw something when it was directly on the rod, not on the cross section. We have time to vent, put that sample in, and then try it.
Yeah, if that's the only thing you think will get it, maybe we're just not getting the depth that we have in the past with this sample. The depth of the silver into the surface.
We had some magnesium yesterday for sure. The magnesium is just part of the glass.
I believe so.
Thought I saw silver. I'm not sure now. How about the other two samples on the holder? I mean, on the puck. This one and that one.
If this is mount 2, those should be, one of them is potassium, so it could potentially have potassium, and then the other one is, well, they all have potassium actually. So they all have potassium, but two of them have 5% silver, and then one of them was in the 5% silver and potassium, but it turned out clear. So the glass composition may be different on that one.
Okay. Yeah, I see that one. Okay, that's what I would try. I mean, let's try that. Let's just I'm gonna replace the sample and put the rod directly, and then we look at it, see if we see something.
Okay.
All right. So what I'm going to do, let me just share that out, is I'm going to stop that line scan. And let me retract the detector. Yeah, we see that bump in silicon too. So it's hard to know what's real or not in that particular case. Okay. So I'm going to go here and turn the beam off and open the machine. It's going to take a few minutes. But I can show you that. That's actually interesting to see. Let me stop that. Okay. So it's a vacuum system. I cannot touch anything that goes into the vacuum without wearing gloves. That would be bad. So we'll put gloves on. Always wear gloves. Without the gloves, you might not reach a good quality of vacuum, and you contaminate your machine and your sample. So you got to be careful on those. So what I'm using is a little holder like this, and I'm putting a tape, just sticky tape, double side, but it's loaded with carbon so that it makes it conductive. So it helps a little bit. I'm going to put the sample on. All right. Let's see if I can turn this. Opening the chamber. You see the samples are right here. I'm going to put the sample like that. Okay. And pumping the machine now. Okay, so it's going to take a couple of minutes to pump, and we'll see. That's research, right? That's when you don't know how things are going. You just have to attack the problem from different angles. And another angle is using different characterization techniques. So, I mean, we're doing imaging. I mean, you're doing imaging just with your eyes looking at the change in color. That's characterization already. And we've done SEM, we've done EDS on the cross section. We couldn't really see the silver. We're going to do EDS on the side, so directly on it. And another technique we have that we'll talk about next week, and I'll try to have data for you, but that's one of the machines that's not working now, is it's XPS. So XPS is X-ray photoelectron spectroscopy. That's another machine we have at the center. And it's also an analysis, a composition analysis machine. It doesn't give you imaging, just analysis, but it's very, very, very surface sensitive. So you probe the first 10 nanometers of the sample. So extremely surface sensitive, and you can do depth profiles, which means that inside the machine we have an ion beam that can actually erode, mill the sample layer by layer, and then you just gradually study the first 10 nanometers of that pit that you are digging, and that tells you, I mean, that shows, you know, maybe transitions, or you can really go gradually through a very, very thin coating or region of interest. So, for example, here, if you had 50 nanometers of silver, that's enough to give you that color. But probing a micron deep, the signal from the silver is going to be dwarfed, so you don't really see it here. But if you go to XPS, another technique, because you study the first 10 nanometers, then the silver is going to be visible. So a lot of materials characterization is trying to find the right technique to suit your needs. And a lot of times you just don't know until you pick one and get started. So let me share this one. Right now, I'm just waiting that this is ready to go. It's a big chamber, so it takes a little while, a few minutes, not too bad. How much we have? Yeah, we have like 15, 20 minutes. Yeah, it's good. That's a good thing about EDS is you get an answer fast. Even if it's a bad answer or an answer you didn't want, you get it in 10, 15, 20 minutes. XPS is another beast. The technique I just mentioned, because it's so surface sensitive, you need to get a very, very high quality of vacuum. And that means pumping for a while, which means that right now what we're doing, the pumping, before we can get started in SEM, we're talking about 5 minutes. In the XPS, we're talking about an hour at least before you can even start, the beam and get started. Because, at some point you have to vent one part of the machine to load your sample in, and that has to be pumped to a very, very low pressure, and that takes a lot of time. But EDS is faster, which is why a lot of people want to do EDS, because that's one advantage of it, is you get an answer super fast. But the drawback is that the interaction volume might be too big or not big enough, depending on what you're doing, and the precision, also the accuracy of what you're measuring, is maybe not as good. So I'm going to use the same settings here, and let's see what we can see here. I hope we're going to be able to see silver. All right, so I'm on the rod. You can see that here. So I'm just going to switch to the EDS PC. I'm not going to do landscape. I don't need that anymore. So this one. Hopefully you see it, like a box. Yep. So again, carbon a little bit. Oxygen, you're gonna have the silicon, magnesium. So just like we saw before, that's on the glass most likely, but right here, silver. You see it has several peaks. So yeah, we have all of them. And the potassium that has an overlap. So you can see it, calcium. All right. So that tells me that yes, you do have silver. I mean, you know that because that rod is yellow, right? I mean, it changed colors, something happened to it. So why we couldn't see it on the cross section? I mean, right now we are probing. I mean, again, at 10 kilovolts, that's what I'm using. We're not going we're going a micron in, maybe something like this. So when you cut and you embed and you polish, the first few microns are disturbed. Yeah, if the silver was penetrating maybe 10 microns in, 15 microns in, we should be able to see that. If it's within the first 5 microns, we might not be able to see that. Stop sharing for a second. What you have when you embed something into the puck is that at the interface, when you cut and when you polish something, it rounds a little bit. And I mean, it's not much. It might be the first couple of microns when not a lot, but that might be enough in that particular case that, it prevents us from seeing that. So, here's what I suggest, and feel free to, we're bouncing ideas here. We have 2 hours next week. We could make it 3 hours, it's fine. What I think we could do is I will try to run a sample like that in XPS. And XPS is not really a nice technique to share because it's, I would show you how to load this sample and then we wait 2 hours for the machine to pump. And there's no imaging, it's just a spectra showing up. So I'll try to get some depth profile or something on it. But maybe what we could do next week, we could try to do a fib cross section and do that line scan on the cross section and see maybe it's 1 or 2 or 5 microns deep. What do you think?
I mean, that works for me. How long does it usually take for the fib? Because me and you have some fib experience doing some other samples, and that took a long time. So I'm just kind of curious on.
If we make a TM sample, it would take a while. If we just do a cross section with a line scan, that should be fairly quick.
Okay.
What I would do most likely in that case, what would be annoying would be the charging effects because of the rod not being conductive. So I would just sputter coat it, so it's easier to handle. And then we'll see that platinum sputter coat, that little thin coating, and below that we will see the silver rich region that we just identified, and then hopefully we see decay as we go in depth. That's assuming that the first 10 microns are what's important.
Yeah, that's I'm gonna guess based on our previous experience with the depths, that maybe we just didn't get. So in the past, some of the really deep ones that we've seen are probably 50 to 100 as our maximum, and we probably just went on the lower end of that. So yeah, I mean, I think it would be, if you think it's useful, if you think it's just like maybe the grinding effect, then that could be something interesting to look at, and that would help us obviously kind of going forward and how to give you samples.
Yeah. Okay. Well, I can just I have the sample in, so I can quickly try that this morning, like half an hour, just cut a little piece and then put the fib and see what it looks like, and then if it's looking good, then we can do a lot of that on Monday. I mean, fib and EDS.
Okay. Yeah, and if that isn't the case, if it doesn't look good. If you don't think it's gonna do much, if you still want to show them the process, that would be fine. But we do have. I gave you those 3 samples. I think you showed
Yeah.
the class. So we do have a little bit that hopefully XPS will show us something. So
yeah, I hope so. Yeah, I think we could do a few cross sections on several samples next week. That would work.
I think that one that you're looking at now is probably the most likely to show us anything for silver.
I mean, it is pretty clear. I mean, it's a pretty strong signal of silver, so it's good. That tells me that it's not just the first 100 nanometers. There's definitely some silver in there. Okay. Maybe a micron or half a micron or something.
Yeah, it just looks like it's just not far enough to see on the cross section.
Yeah, I guess my just the grinding probably like maybe broke that tiny region. Yeah, if it was 50 microns in, we should be able to see it, but we can't.
Okay.
Okay. We have a few minutes. Should I just quickly talk about explain what we're discussing about the field? Because I mean, it's not clear for everyone.
Yeah, I think that could be useful before we run out of time here, just to kind of go over that so that you can kind of just jump in next time.
Yeah. So let's talk about our plan. Oh, I was looking at something else. Field cross section. So I mentioned earlier at the beginning of the lab that this is a FIB SEM, not just an SEM, it's a FIB SEM. So it has another beam. It's a focused ion beam. That's what FIB means. And a focused ion beam is really used in a machine like that to shoot heavy ions, gallium ions in that case, shoot ions to the sample, and it's going to mill the sample away. So you can make cuts, any cut you want. And it's small scale, right? It's meant to be for the micron and sub-micron scale. But in that case, it's a good application. And this is what it looks like. You can have, actually, I think that's just doing my stuff, but this is on gold. And it's cutting a little bit, and you see the cross section. So the original surface is everything that's around here. And then the surface protected by a little pad, and then you cut perpendicular to it with the FIB, and then you see the cross section. Trying to see if there's, that's perfect. Yeah. That's what we can do. We have the SEM vertically, that's what we've been doing today, but we have the FIB at an angle. So that's exactly what we have. And we can tip the sample, and with the FIB, pretty much remove all of this. And then the cross section that's here can be viewed by the SEM. And that's what you see here, okay, that whole cross section. So on the sample we have right now, the glass rod with the silver, in it, we could make that cross section and run EDS on that face here, and we could see the first, you see the scale bar. You could see the first 5-10 microns, pretty much pristine, right? There's no grinding or anything that's damaged it. So hopefully, if the silver-rich region is only a few microns, we'll be able to see that on preparing the sample that way. So that would be the plan for going forward, because we know we have silver at the surface, but how deep is the question? And it sounds like from what we've done today that it's not 50 microns deep, but it's at least a few hundred nanometers or microns deep. So that would be a way to investigate that next week. Yep. Okay.
Sounds good.
All right, let's do that. So I'll prep the samples a little bit and try to do XPS as well. I'm fighting with the machine right now, but hopefully it's good enough to do that. And then I think, the FIB could be a good thing to do on those. Okay. Any question? If you can, you can ask questions, by email if you want to bring them next time. Please don't be shy. Like really ask questions. I mean, it's pretty straightforward, I guess. But try to keep in mind what's important to keep in mind with those techniques is the signal that are being used, electrons or X-rays, interaction volume is very important. You know, how deep, everything we've been discussing the past 20 minutes is all about interaction volume. You know, what is the volume that you are actually probing? It's very easy to say, oh, I'm just going to look at the surface, but you know, the surface means different things. If you talk to someone who runs XPS, the surface means the first few layers of atoms. If you talk to someone else, it's going to be the first millimeter. So different techniques probe different volumes, and that's something to really know and understand. So in that case, I think EDS on the cross section didn't really work. And now that the sample is on its side, we don't really see the depth, right? So we'll try to have some answers next week. All right, well, we'll stop here then, and I will send you the video as soon as I download it, and then you can share with everybody.
Okay. Yeah, I'll do that.
So did we say I forgot, Monday or Wednesday morning?
Yeah, let's do Monday if that works okay for you.
9 to 11, same thing. Yeah, that'll work.
Yep.
All right, well, see you all on Monday. Thanks
all right,
for
thanks, Nico.
tuning in. Yep. See you all. Have a good weekend. Bye.